Hi, Year 11s. Today we're looking at general solutions of sine, cosine, and tangent functions. So rather than just finding a solution in a domain, we're finding all of the possible solutions, and we're going to be defining it by using n, just some integer that's defined for all integers. So if we start by looking at cosine of x equals a half, our next step to solve this would be to take the inverse cosine function of both sides, which gives us x is equal to inverse cosine of a half. Now, if we were to go to our class diagram and get our two solutions for that, we would get x1 equals pi on 3 and x2 equals negative pi on 3, which is also known as 5 pi on 3. So that just comes from the fact that 2 pi minus pi on 3 is 5 pi on 3. And similarly, this is going to be 0 plus pi on 3, because we started our positive x-axis, and then we're going counterclockwise pi on 3 radians. So if we were to look at these two approaches to our answer, we've got 0 plus pi on 3 and 2 pi minus pi on 3. We can see a pattern's going on here. We're adding pi on 3 or we're subtracting pi on 3 from our period. So we have a property that we'll look at over in this space here. If you have cosine of x equal to some number a, then our solution is going to be inverse cosine of a being added to or taken away from 2 pi times some n, where n is an integer. So we can see no matter what n we put in here, 0, 1, 2, 3, whatever, -1, -2, so on and so forth, we're going to get all our solutions here. We're going to either add or subtract the inverse cosine of a. So in our case, that would be 2 pi n plus or minus pi on 3. And if we have a solution like this with a fraction, we can go one step further and factorize out the pi on 3. We're going to get pi on 3 times 6n plus or minus 1, where once again n is an integer. So generally when doing solutions like this, we'll say that n is an integer when we first use the pronumeral, and then we'll remind the reader that n is an integer in our final step. But you can see in this 6n plus 1, that's going to give us numbers like 7, 5, it's also going to give us 1 and -1, just based on whatever we put in as our n. Okay, let's move on to the next question. Okay, so what about the general solution to tan of x minus pi on 4 is equal to square root of 3? So what we're first going to do is a variable transformation. Let theta equal x minus pi on 4. That's just going to help us clean up our initial equation, and then we can substitute it back in later. So tan of theta equals root 3, which means theta is going to be the inverse tan of root 3, which is going to be pi on 3, and pi plus pi on 3. So that comes from our cast diagram. We're going to have pi on 3 this way. We're going to have pi on 3 here. So if we add our 180 degrees to that, we're going to get pi plus pi on 3. So we can represent this as pi on 3 plus or minus pi n. So because of this property of the tan function, we're going to have solutions periodically at pi rather than 2 pi. So all of our solutions are going to be symmetric to each other by 180 degrees. But we're not done here. Now we need to substitute back in theta equals x minus pi on 4. So x minus pi on 4 equals pi on 3 plus or minus pi n. So x is going to equal pi on 12, 7 plus or minus 12n. That just comes from adding pi on 4 and pi on 3. If we make them have the same denominator, we're going to get 7 pi on 12. Okay, next question. Determine the general solution to square root of 2 sine of 3x plus pi on 4 plus 1 is equal to 0. So let's manipulate this to be a little bit nicer, and this time we're not going to do a variable transformation. We're going to see what happens if I just leave it as 3x plus pi on 4. So different approaches that will give you the same answer. So let's manipulate this so that we just have sine on the left hand side. So sine of 3x plus pi on 4 is equal to negative 1 on square root 2, which, as you know, is also negative root 2 on 2. Then if we take our inverse sign, we're going to get 3x plus pi on 4 is equal to inverse sine of negative 1 on square root 2. And so we get 3x plus pi on 4. Not sure what happened to that 3. Let's fix that up. Plus pi on 4 is equal to either 7 pi on 4 plus 2 pi n, or the other solution that we're going to get is 3x plus pi on 4 is equal to 5 pi on 4 plus 2 pi n. So two possible solutions based on where you're looking at in the cast diagram. So if we do some simplification on each side, our left-hand side is going to end up as 3x equals 6 pi on 4 plus 2 pi n, which means x is going to be pi on 2 plus 2 pi thirds times n. What have I forgotten to do up here? I need to introduce my n as an integer, so n is an element of the integer set, and then I'm going to factorize out pi on 6 from both of these terms, and we get 3 plus 4n. Now, there is a couple different ways to represent this bracket. Because n is an integer, we can rewrite this, and this is what the textbook solution is for this question. We can write that as 4n minus 1. That's just sort of taking all of our n values and shifting them over by 3, and then that's going to give us this new set of solutions that's 4n minus 1. We can see that it's the same. If we put 1 in as our n here, we'd get 4 plus 3 is 7. We can still get that here by putting n equals 2. So 8 take 1 is equal to 7. Okay, let's look at the right-hand side now. So we're going to get 3x equals 4 pi on 4 plus 2 pi n, which means x is equal to pi on 3 plus 2 pi thirds n, which is going to give us 2n plus 1 pi on 3. And that will give us the answer of pi on 6, 4n minus 1, or 2n plus 1 pi on 3. Don't forget to also reintroduce the fact that n is an integer. So two sets of infinite number of solutions, depending on what value of n you choose. Okay, that's all for this video. Thank you.